Hello, this is Iron Designer here. So I just wanted to make a video that goes along with another video I made some time ago on pull-out shear, and I'll show you the thumbnail later, but it has over 8,300 views on it, and I think this video is also going to explain other types of failure. So I just wanted to get into making a follow-up video to that previous video we looked at before. Alright, so it just needs to be clear that bolts are used in all sorts of designs, and sometimes the mode in which the bolt is used could be combined loading, which means in a plane there's X and Y directions of force. There could also be rotational shear on the bolt pattern, and you could combine all of these different modes of stresses onto the bolt and the bolt pattern. There could also be a moment applied to the bolt. There's axial clamp load applied to the bolt, shear loads, torsional loads, etc. So any of these combinations and maybe more are all the forces being applied to the bolt, which is typically in tension, and that's its main mode of effect and service while it is being implemented. So now I just wanted to take you to the thumbnail that has over 8,300 views. It's called Pull-Out Strength, and I went through an exercise where all the bolt is doing is it's just being ripped out axially from the connection. And I went through a lengthy explanation using the theories by Shigley and in Shigley's textbook. And so if you're not familiar with that, go take a look at that video, as well as finishing up this video. So here I just want to talk about just a few of the failure modes. There's many more, but I listed here 10. You've got stripping of the threads, which is the pull-out strength video. There's over torquing and over tightening of the bolt, which what that does, it begins to fray away at the threads. So you're galling the threads if you over tighten, and you're weakening the pitch diameter. You also have pull-out shear, which is similar to stripping the threads. You have just single plane shear, which is cross-sectional to the axial load. So now you have axial load stress, and you also have perpendicular to that shear load stress, and that could be bidirectional. So you'd have to find the resulting vector. You also have bending on the bolt. So in some cases you may have a cantilever connection and the bolt is in axial stress, and additional axial stresses are applied to the bolt as a result of, say, cantilever bending. You also have double shear, which is what you would have in a yoke pin or something on the shank. And you can even have triple shear. You just add an additional yoke to the first yoke, and now you can have triple shear. So there's many modes of shear. You could even have bidirectional double shear. You could even have bending stress double shear. You could have pull out double shear and bending. So you could combine these modes in as many ways as you can think of, and there are many more than this. You could also have fatigue loading, which means that you're applying axial stress and removing it, applying axial stress and removing it, applying it again and removing it. So using the bolt almost like a rubber band. You know, even though the bolt is fully clamped and fully torqued to the specifications, you could apply additional axial fatigue to the bolt. You could do combination loadings, as I've talked about before. In fatigue, you can also have reverse and repeated loads. So you could say if you're pushing on shear in one direction and then pulling shear in the other direction, and then pushing again in shear in the first direction and pulling back again in the opposite direction, that's called repeating and reversing fatigue loads in shear. And then you could have vibrational loads, so just making the bolt chatter at a high frequency could damage the internal structure of the bolt. And then number 10, you could have under-tightened bolts. So the bolt is kind of slopping around. It could be involving bending shear, double shear, simple bending, axial tension that's being applied and released. So it's like bolt chatter, and that's another mode of failure. So I just wanted to go over just a basic brief failure modes list. It's not comprehensive. There's many more, and you should take a look at the pull-out shear video in my playlist. Go take a look at that. It's got a very extensive analysis using the methods of Shigley. So what I wanted to go over in this slide is just to look at just a couple very simple modes of failure that are fairly common. And we need to go over the different nomenclatures of the bolts so that when we have a discussion about failure or engineering analysis, we use the nomenclature correctly. So in the blue box, you have the head of the bolt, okay? And then under the head, you have a radius. That just comes from manufacturing, and it's best to have a radius and not a perfect sharp corner, because that would be a whole nother video on stress concentration factors. If the radius went to 0, you would have almost infinite stress concentration. So they put a radius in there in order to limit the stress concentration to maybe a 2 or a 3 rather than 25 or 40. You know, it'd be much higher. As the radius gets smaller, the stress concentration goes up. Then on down, you have the shank. The purpose of the shank is to have the maximum diameter of the bolt. So if the bolt is in shear in the shank, in the length of the grip length, you're going to have the strongest amount of diameter material in the bolt. So that's the purpose of the shank. Instead of just threading the entire bolt all the way up to the head, you leave some shank, that's called the grip length, and you just tighten up to the grip length so any shear potential comes in the shank. After the shank, you have the runout. Now the runout is where you bring the shank down to the root of the thread diameter. And so when you have a thread, you have the root of the thread, the outside of the thread, and approximately halfway above and below the thread, you have what's called the pitch diameter. And I talk about pitch diameter in the previous video, pull-out strength, so you can look at that. Then you have the nut. The nut is what's applying the clamp load using torsion, right? So as you torque the nut, then the bolt begins to stretch due to tension in the bolt. You have tension in the threaded length, and you have tension in the grip length. So remember, the grip length is primarily to oppose shear, but no matter what, you still have the nut on the thread length, so you're still going to have stresses in the runout, okay? Then, of course, you have the threads, and the overall length of the bolt is measured from the bottom of the head, and that's called the nominal length. So if you take a look here in the red box, you can see an example of over tightening a bolt. It was over tightened so much that it began to neck down. So that's called necking, when the bolt diameter begins to shrink, like say plastic putty or something. When you pull on it, it begins to shrink in the middle, and the steel much stronger than putty, but the deformation is called plastic deformation, and it behaves the same way. In the orange box, we see two different types of shear failure. You have in the upper left corner the single plane shear failure. In the upper right corner, you have the double plane shear failure. But as I mentioned in the previous slide, you could even have triple plane shear failure. So if you just double the upper right hand image and add more plates to it, you see how potentially you could have triple plane shear failure. And then the rest of the diagrams A and B just show how the failure mechanics work. So you can see the mechanism of the various shear. Now here in this slide, we're going to talk about a few examples of the basic modes of the failure process, and we're going to begin to apply vectors and magnitudes to the vectors. So the vector has a direction, and we're going to find out the magnitude of the vector. Usually we'll represent magnitude by the length of the vector, and we give it a direction. So we're going to use trigonometric and geometric principles in order to break down the components into perpendicular X and Y resulting forces. And in the upper left box, the green box, you can see I'm just showing a few examples. You could have bolt patterns with 4 bolts, 5 up through 8, but it could be any number. If you look at the blue box, you see they have here a rectangular shaped bolt pattern with a centroid in the center with the red circular arrow, and then you have the two perpendicular forces. So you have combined loading. You have torsion on the bolt pattern from the moment, and you also have directional loads. So you have a complex combined loading in that diagram. And you know, it really doesn't have to be in those directions, but they just did it for convenience so that they could break the components down into vertical and horizontal perpendicular axes of components and shear. If you look to the right, they're using their 8 bolt pattern. So there's a moment being applied to that pattern of 8 that's kind of vertical. And what they've done is drawn lines through the centroid. So from the center of the bolt through the centroid, and then the moments are acting opposite, or the reactions in the yellow arrows are acting opposite to the direction of the moment to resist the moment, and they're acting perpendicular to the center lines drawn through the centroid. So this is just one diagram showing you only torsional or moment, basically. The one to the left is showing combined load, moment, and directional loads. If you look at to the right, the diagram, the geometric definitions, you can see in that case the load is coming in perpendicular to one of the bolt centers and is not passing through the centroid. So that would have to be analyzed differently. So you've got the center of inertia, IC, and you've got the centroid or the center of gravity, CG, and you see there's an angle of the force load P acting through the inertia centroid, And that's what I was saying before, that your loads don't necessarily have to be vertical or horizontal. They could be at any angle and in any direction. They could be forces coming in even in a third dimension. So it doesn't have to be planar like X and Y. It could be X, Y, Z. So that's what's being shown in that little thumbnail there. And the one below that, it's just showing a simple vertical load that you would think is only a shear load, but there's actually moments created, and the engineer needs to study if the moments, the reaction moments, are greater about the upper bolt or the moment reactions are greater about the lower bolt. And I'm not getting into that analysis in this video. I'm going to stick here with just bolt failure modes. To the right, you have some designs there where you put the rods inside those parts and tighten down the screws, and then those rods are in tension. So the bolts are in shear when the rod is inserted, and then you have the yokes, which are bolted down or attached a different way. So that's a product, some kind of a shear bolting product, maybe for fast assembly out in the field without welding or having to drill all the way through. They're just relying only on the pressure applied by the bolt creating shear. Then below that, you can see an example like I showed you before. You had the necking down, and here you see what's going on is you're beginning to go through the process of shear with this bolt by moving the threaded length away from the shank length center line, so their center lines are no longer coincident center lines. And you see the location where the shear is happening. It's exactly in the run out. So if you remember from the previous slide, we specifically talked about the run out being kind of a danger zone to the bolt. So what I've done here is I'm just using Microsoft Excel. You can tell it's an old version of Excel. But the important thing is that I'm creating my own analysis. So the example that I created for myself here, pretend you're an engineer and you have a circular disc with 4 holes in it, and they're equally spaced, they're geometrically and symmetrically equal. And what you have here is this data given to you to analyze. So assume that the torsion, which I put as X, is 3,300 foot-pounds, and I made the X kind of blue. And here are the components of the 4 vectors that relate to X. Not this one, but this one, here, here, and here. So you take that and you divide that by 4, because we're assuming that each of the bolts is going to carry an equal amount of load in rotation. And then you have the force F, which is this one, and I'm saying that it is a vertical force, and it is 1,900 pounds, and I colored that in orange, and here's the orange vectors for F. So I'm assuming that each of the 4 bolts are all equally distributed and symmetrically carrying the load equally among the 4 bolts, and so I take and divide that by 4. Then I have a force E, which is a horizontal force, E. I colored it green. And here are the green arrows, 1, 2, 3, 4, to represent the breakdown of E. And I'm also saying that in the direction of E, that's what I'm calling the positive direction, okay? And in the direction of F, which is vertically up, I'm calling that the positive direction. And likewise for X, which is the torsion or the rotation, I'm saying that the counterclockwise, okay, is positive, okay? So now we create a little table here. You have bolt A, bolt B, right here. This is bolt B. See the arrows pointing toward B. This is bolt A pointing toward A. This here is bolt C, and this here is bolt D, okay? So A, B, C, D, okay? So this is pointing toward D, that's D. This is bolt A, bolt B, and bolt C, okay? Bolt A, bolt B, bolt C, bolt D, all right? In that direction. So now, the rotational Y direction of A, all right? So A is turning counterclockwise, and the rotational of A, since this is shown this way, these are like at 45-degree angles. So if you take the square root of 2 divided by 2, it's 0.707. So if you look inside this cell, I get the value C16, which is the 3,300, divided by 4, because there's 4 bolts, and I multiply it times 0.707, because I'm trying to find only the Y component of the vector perpendicular to the centroid. So I'm just finding a vertical vector for this blue, these blue arrows, okay? And since A, his vector is pointing in the positive direction up, like F, his value is positive. Then you go down here, B. His vector, perpendicular to the centroid, is in the positive direction. So that's B, positive. Bolt C is pointing in the negative direction relative to F, because we're only talking about Y directional components. So C is negative. Bolt D is this bolt right here, pointing downward. His Y component is in the negative direction. So negative. Now you do the same thing for the next row for the X direction. So that would be relative to E, okay? Just like the force E coming in horizontally, all right? Force F was coming in vertically. Torsion X is on the centroid turning counterclockwise. Okay, it's very important that you understand that. Now the linear component of F by itself, remember F is orange, and broken down divided by 4, there's F. So each of these orange arrows is 1/4 of this value. If you look at here and you look at the cell, you can see it is C17 divided by 4 all the way across. So this whole pattern is positive. Next with E, we do the same thing. If it's pointing to the left, then it's positive. Okay, you may choose a different coordinate system, and that's fine, but you need to be consistent. So here you have the same thing. You have value C18 pointing to the left divided by 4. Okay, so there's 4 of them right there. Now we want to do the summation of the forces in the Y direction. So we combine linear F with rotational Y, okay? And we get these two values, see C22 and C24. This here is C22, and here C24. So that's the formula. We copy that all the way across. Yes, sometimes it's going to come out negative. You do the same thing for the horizontal forces. Remember, to the left is positive. So we combine C23 and C25, which would be this one and that one, and we get those values, and we copy that all the way across. Now we want to find the actual magnitude of the X and Y summation of the forces. So we use the formula A squared plus B squared, take the square root. Okay, so that's the formula that we use. We copy that all the way across. So now we have these values here. These values here in the yellow strip. These values are figure 2. So I wanted to make this diagram here to show you just graphically the magnitude of the 4 values. These are the resulting magnitudes of the values. So A, B, C, D. A is the strongest, okay? You see, not always is everything going to be equal, okay? That's why bolt patterns fail, because engineers need to do analysis much deeper than just a visual symmetrical symmetry geometry analysis. You need to do the trigonometric, the algebraic, and the calculus analyses, okay? So it's just a little thumbnail here showing you forces on the yellow strip. Now we want to find the direction of those magnitudes. So we just use the formula that tangent equals rise over run, okay? Rise over run. So rise would be the y value, that's the rise, divided by the run gives us the radians. Okay, at first you just need to do the radians. Then you convert radian into degree, okay? And then in figure 1, which is here, I just brought in a protractor, an image of a protractor, and I began marking down the vectors on the protractor just so you could see in what the direction is of the resultant vector, okay? Now, this is what gets students confused. Each one of the bolts is going to have its own coordinate system, okay? So depending on the coordinate system you're in, you're going to have, of course, since this is going in the counterclockwise direction, I've shown the vector directions also in the same coordinate system counterclockwise, okay? What this is showing you is the perpendicular or the normal to the resultant in the same direction and same coordinate system as the rotational coordinate system. So when you look at the angles, say this one here, bolt A, here bolt A, why is it going in this direction? Because at an angle of 46 degrees, which is from vertical to the left 46 degrees, and that's what I'm showing here on the protractor, you go from 0 up to 46 degrees. You can see the 40 and the 50 right there. And that vector has to be perpendicular to this angle that's found here, okay? The same thing is resultant for, say, green, which is D. The D value is -6 degrees. So 90 degrees over from A, 90 degrees over from A is D. So you rotate your directional vector, and at -6 degrees, so it'd be to the left, right here, you would have an angle of -6 degrees with the magnitude of 1,026 pounds force, okay? And you just repeat that again. You go to the left, You have another angle here of 36 degrees. You index the angle 36 degrees and you show your resultant force perpendicular to the angle according to the force diagram right here. So that's 36 degrees, and the magnitude is only 181 pounds. And that's simply because what we're doing here, this analysis, is just an instantaneous analysis. And likewise for B, you have A, B. B is also at an angle of 82. So his angle is going down in this direction, 82 degrees, not quite 90, but a few degrees away from 90. The vector of B is in this direction, and if you drew the line straight up, it would be perpendicular to the magnitude, okay? And that magnitude would be 1,068 pounds at negative 82.16. So you see, it's negative direction, okay? Because we said that the positive direction is counterclockwise. So if you're going opposite to your coordinate system, you'd be going negative. And that's why this value is negative and the radians are negative. So you see everything, you know, checks out mathematically. So that's negative, and there's the magnitude. So I hope that explains this example. I know some of these are very complicated even for just 4 bolts. But if you do a spreadsheet and you kind of think of everything logically, you can see that according to the angles, according to the vector directions, according to your coordinate system, that's how the analysis should work out and make good sense when you are doing your engineering design. So lastly, I just wanted to wrap it up. I always like to put in a conclusion in the videos if possible. So we started off by talking about how bolt patterns fail and why they fail and their modes of failure. That was how we started this discussion. So our conclusions are, after reviewing the analysis page, is that vectors will take on various magnitudes and directions depending on their positions at the instantaneous time of analysis. So if that pattern was rotating or vibrating or in a reversing condition, you would need to take multiple analyses at each instantaneous point of time in your analysis, okay? So you might have a frequency analysis or a load, you know, peak minimum, peak maximum analysis. You need to somehow decide, is it a static analysis or is it a dynamic analysis? Number 2, reaction vectors must be computed from at least 2 perpendicular input vectors in order to use the Euclidean geometry and trigonometry to define the resultant vector, and I explained that. If there is additional combined loading, such as rotational force, those two will need to be separated into their own vector components and combined into the sum of forces equations. Number 4, all forces in the instantaneous analysis will need to be combined into the summations to compute the final force vectors. Number 5, the bolts will cycle their load magnitudes as they move through their load cycle distribution. So I just talked about that. The example only shows one instantaneous moment in time for the bolt pattern. What if that moment is variable? What if it's being applied and then reduced? And what if the moment is then being reversed? So that's what I'm talking about, different modes of analysis in the instantaneous time. Or what if force F is sort of like increasing, then decreasing, increase and decreasing? You need to find out at what point are you looking at maximums, minimums, averages, and what's the frequency? Do you apply fatigue analysis? Number 7, forces have continuously changing load cycle and loading frequencies depending on the rate at which loads enter and exit the bolt pattern system. Number 8, the engineer should examine numerous phases of the loading cycle to determine the true maximum loads that input, and also not only minimum loads, but if the loads reverse at any given time, or if load reversal is part of the loading cycle. So I just wanted to mention that if you read the chapter in Shigley on fatigue, you'll notice that you don't need to be at maximum load in order to have fatigue failure. Fatigue loading and fatigue failure is only dependent on the frequency of the applied load. So take a look at the fatigue chapter in Shigley. I use version 10, the 10th edition, if you wanted to know. If the load reversal is part of the loading cycle, number 9, then the engineer must change their analysis from a combined loading cycle to a combined fatigue loading cycle and add more knockdown factors to their safety factor above and beyond the combined loading cycle safety factor. So I just talked about that. The engineer should design an analysis tool such as this one, but incorporate continuously changing variables in the tool so the tool can cycle to a full 360 degrees, okay? Or just the full spectrum of load. The design engineer should also incorporate a full cycle reversal in their tool to verify all combinations of loads and forces in the complete cycle of their model. And lastly, as a sanity check, the design engineer should determine if the input loads actually reflect the limits of the loading to convince themselves that the resultants cannot be exceeded in the actual design. So I hope this video helped you out. It might have been a bit lengthy, but this is a complicated analysis section in engineering. And this is Iron Designer, and I am out. Thank you very much.